Okay, let's review the concept of work. Again, we're going to attack each one of these concepts and then talk about it in our different systems. Now, first of all, our definition of work is literally we have to use a force or a force-like quantity to move something. And that's kind of one of the key characteristics of work in ours, is we physically have to move something in order for it to happen. In a mechanical system, it's objects that are moved. In an electrical system, it's electrons that are moved. And in a fluid system, wait for it, it's fluids that are moved. So in each case, we have to have something moving. And that. Now, math gets a little more complicated. Let's look at mechanical systems in greater detail. First of all, there's, again, two different types. We have linear and we have rotational. So let's do those separately. In a linear system, work is equal to force times displacement. The key thing is F and D have to be in the same direction. And that's kind of important. So I do work when I pick a book bag up, but I don't do work when I carry a book bag. There's no work being done on a book bag. So if I'm displacing it, if I'm displacing it that way, but the force on it is that way, by our definition for science, that's no work being done. Key thing to understand is F and D have to be in the same direction. If I have this, F is that way, and D is that way, that's work. But there's no work if I do that. Also, no work if there's no displacement. So holding something is not work. Now, for my units, real quick, well, it'd be the units of force times the units of time. So therefore, in the English system, well, the units of force are going to be pounds times feet. And again, I don't care whether you write foot-pounds or pounds-feet. I see it written both ways. For a long time, we had the convention that we were going to write pounds-feet for work and foot-pounds for torque, but I don't know that it really matters. In the SI system, it's going to be newtons times meters. That is not a joule. It's a newton times a meter. Oh, excuse me, it is a joule. Never mind. I'll go back to sleep. Now, for rotational, work is equal to torque times theta. Now, here's one of the key things that we need to understand. Theta has to be in radians. Has to be in, remember, 6.28 radians around any circle. So 2 pi is equal to 360 degrees. 2 pi is radians. You may not have said that in math class, but that's really what it is. Torque is force times lever arm. Now, one thing to, if I'm talking about things that rotate and do work that are round, something like a winch, that's your force. Your lever arm ends up being the radius of the wheel. So it's important to understand that. Second thing is, again, they're gonna test you with this. You will have to be able to go to revolutions per minute to radians per second. That's something you have to do. Now, if you can remember this, 1 revolution is equal to 6.28 radians. And of course, you know that 1 minute is 60 seconds. You can make that conversion. So if you had something like 10 revolutions per minute, put revolutions on the bottom to get rid of them, radians on the top, 6.28 is 1 revolution. Now, if I stop right there, I would have radians over minutes. So I got to get rid of that. I put minutes on the top. I put seconds on the bottom, 1 and 60. So I'm going to have 10 times 6.28. So I'm going to have 62.8 radians on the top divided by 60 seconds. So a little over 1 radian per second, approximately 1.05 rads per second. So that's something else you're going to be expected to be able to do. Now let's take a look at a fluid system. In a fluid system, there's two ways I can write it. Work is equal to P delta V or delta P times V. Either one of those will do in work. Again, I have to move a fluid to do it. Now I can move a different amount of volume of liquid, or I can move the same volume by changing the pressure. Either one of those will work, and understand it's important to do that. Now, when I take a look at the units, this actually reduces down to force times displacement. So you get a shortcut with that. It's always going to go from high pressure to low pressure. The biggest place we see fluid work being done is pumps. And pumps are around us all the time, whether we're talking about water pumps in your backyard to get water out of the ground, whether we're talking about pumps owned by Broad River Water Company, whether we're talking about a steering fluid pump, or a water pump in your car. Pumps are around us a lot. And work is equal to pressure times volume. Now if I take a look at the units are exactly the same. In the English system it's pounds, feet. In the metric system it's newtons times meters. Now you can get that out of if you say this pressure is going to be pounds. Let's make it pounds per feet squared, and then volume would be feet cubed. That reduces down to that. So the units are still the same. Now the other thing that comes up in fluid systems that we need to understand is the concept of weight density. And again, it's a different concept, and it's a concept really only used in fluid stuff. Weight density is nothing more than the number of pounds per feet cubed, or newtons per meter cubed. It's weight divided by volume, and again, it's something that you may only encounter in this class, but it's kind of important. Weight per volume is important if you're going to start moving fluids. For example, if you're going to move a fluid up a hill, you have to have a pump that you're going to raise it from this height up to here. Let's say this is your house. Let's say this is the bottom of your well, your pump. In order to figure out the work that you need to do, you're going to need to know the weight density of the fluid to get it. Now, in an electrical system, work is equal to Q times V. It's charge times voltage. Remember, there's two things that are important in electricity: the number of electrons move and how much energy or force each one takes to move. Now, Q is measured in coulombs. Again, that's that 6.25 times 10 to the 18th coulomb number that you need to know. Volts is measured in volts, but a volt is a joule per coulomb. So when I multiply these together, I'm going to multiply coulombs times joules over coulombs. Coulombs cancel out. I get joules, which is a Newton meter. There is no corresponding English unit. For this, we always measure work in joules. It's actually related to watts, which is kind of funny because you've been using watts your whole life without ever realizing it was a metric system, metric unit. Now, there's another equation that comes out of this that we've been using in labs a lot without necessarily realizing it, and that is I. I is current. We will study it in greater detail in a little while. I is equal to Q divided by T. Q is charge, electric charge, per time. The amount of charge per time, well, it's going to be coulombs per second, and that's what we call an amp, named after ampere. So it's something, you think about it, we've measured that in quite a few labs recently, in the fact that we've measured how many amps the motor is drawing. So that's important. So I is equal to Q over T is kind of a bonus equation, Again, we'll cover it later. So that's an equation you have to be able to handle. Q is going to be charge in coulombs, T is going to be time in seconds, I is going to be current in amps. So we might want to write that over there. It's abbreviation for amperes, again named after a person, but we usually drop it and just say amps. The equations you need to be able to use, and again, you'll be given all the equations, you just have to be able to use them. W is equal to Q times V, W is equal to P delta V, and then W is equal to FD, and W is equal to torque times theta. Now, another thing that's going to show up continuously, so we might as well cover it now, we'll see it a lot, is efficiency. Efficiency is equal to work out divided by work in, and then we multiply times 100 to make a percentage out of it. The max you can have is 100% efficient. Most you can ever have. The minimum you could have would be 0. That would be a broken machine. A lot of machines have fairly low efficiencies. If I can improve the efficiency of a machine, I make it big. I make big money off it. Now, one thing you have to understand is you're going to lose work. Almost in all our cases, almost all the lost work is turned into heat because of friction. If I can minimize friction, I can increase the efficiency of almost every machine we ever use. So again, heat's the big thief. If I can control heat, I can control systems. So what I want to do is I don't want to waste heat. Waste heat is wasted energy, and wasted energy is not good for me. Okay, that'll wrap it up. That's what you need to know about work.